Hey there. So let's talk about constant velocity motion. This is going to be the first model that you'll be dealing with, and it's the simplest. So we're just talking about motion at constant speed and in a straight line. So if it's constant velocity, remember velocity has both speed and direction, or magnitude and direction. So it's got to be constant speed and it's got to be a straight line. In other words, it's not changing direction or speed. So not changing speed or direction. Simplest type of motion, speed or direction. Okay, and that's constant velocity motion. So if we look, this is a motion diagram of constant velocity motion. And remember, this shows displacement. So this is my delta x here. And so what I can see is that my delta x is the same throughout. That's what defines constant velocity from our motion diagrams. In addition, we know that for a motion diagram, the time between these dots, the delta t, is also the same. So the change in time is the same between dots. So we have the same displacement, the same time. And if we graph that, if we graph our displacement over time, we end up getting a straight line. This is time, so for instance, from this point to this point, my delta t would be from here to here. This would be from t initial to t final. And then for x, it would be your initial position and your final position, just for this little segment. And so what we can see is that the displacement over the time, which is my velocity, is the slope on a position versus time graph. So if I kick over another unit, so if I go another same delta t, I get the same delta x. That's what makes it a line. Same delta t gives me the same delta x. And this will change when we look at acceleration. Let me show you just so you have a counter example. So if I had a position graph like this, so if this was my position over time, then every time that I kicked over the same unit, so my delta t, so I get this little piece. If I go over the same amount, I can see that I get more delta x. So the same delta t gives me more change in position, or more displacement. Go over and up, and I see I get a whole bunch more. It's this delta x or the rise, that causes the graph to curve and give me this, I have a changing displacement over time. Anyway, we'll get to this when we do acceleration. Right now we're focused on constant velocity. So we can define our average velocity as the change, or the displacement, the change in position, either x or y, over the change in time. And it's convenient because if I have a position graph, I just get the slope. The slope of the position graph is the velocity. Now we're talking about average velocity here, and in physics 1 we'll keep that. Physics C, we're going to get into instantaneous velocity. But since we're talking about average, we can just simplify it to just Vx or Vy. So V in the x direction or V in the y direction. And remember that just because I use these subscripts doesn't mean this is still a vector. Using the subscripts indicates that it's a vector. So Vx is the same as Vx. Right. Okay. An object's speed. So we talked about this before. The speed, which we can just write as a v without any kind of indicator. It's the magnitude, or just the absolute value of the velocity. In other words, there's no direction. Sorry, my phone rang. That's annoying. All right, where was I? Oh yeah. So no direction. The speed. So we just take the absolute value. So for instance, if I had a position versus time graph, so we're doing position over time, and I had a negative slope, and so I calculated whatever that was, I found my delta x, delta t, and say I got a velocity of negative, 2.3. Well, then the speed, that would be in the x direction. The speed, v, or I prefer to always use the absolute value symbol. That way I know that I'm talking about the magnitude of the velocity, would just be 2.3. We don't care about the direction. Okay, not a big deal. Example. So let's look at a graph of a position versus time. The slopes are marked. And what we want to do is we want to draw the car's velocity versus time graph. So we want to be able to go from a position versus time into a velocity versus time. I'm going to do it down below. It might make it a little easier. We'll see how well I can draw now. Terrible. I think I'm just trying to be too neat. All right, let's just go fast. Yeah, there we go. All right, so here, sorry, this is not x. So we have the velocity, and that's going to be in meters per second. Why is it meters per second? So let's just think about it, yeah? So going back, let me go back up here. The velocity is delta x over delta t, the slope. So the units here on my position are meters. So I end up with meters over time is in seconds per second. So it just makes sense. It's a ratio built out of these two. Okay. Anyway, let's go back to this. So time in seconds. So my velocity. So basically from time 0 up to time 2, we have constant velocity because it's a line and it's at -2. So my velocity for this time period is at -2. So I would go to -2 and up until 2 seconds, my velocity was -2. So that would be a horizontal line for the velocity. When we get here, the slope is 0. So does that mean that there's no velocity? No, it just means that the velocity is 0. So at this point, it somehow instantaneously jumps to 0 meters per second, which isn't going to happen, but, you know, we're idealized. So it's going to be at 0 for a while, up until just before 5 seconds. Oh, I'm sorry, I missed that. 4 seconds, my bad. 4 seconds. Okay, so it's 0 up until this point, and then it now becomes positive and it jumps to 5. So again, it magically jumps, my graph's not to scale, it jumps up to 5. So we can draw a little dotted line up to 5, and then we go like so. So there's my velocity graph for this position over time graph. The car's motion. So the car was moving, since it's negative, if we drew, this is in the x direction. So here's my origin. So the car started at the origin, and then it had a negative velocity. So it was moving away at -2 meters per second. And we could put like the velocity is -2 meters per second. So it goes this way, and if we did one every second, it did that for 2 seconds. So 1, 2. Yeah, same size because it's constant velocity. Okay, and then it was 0. So it was 0 for 2 seconds. So what we do is we can just draw it up above. So there's 1 second, 2 seconds. After 2 seconds, it then started moving back towards the origin at a velocity of 5, positive 5. So this was negative, so it goes left, and then we start moving back to the right. And it's at 5, so we need to draw our vector longer than the 2. So it would be something like that. Yeah, so that will finish out your motion diagram. You could do another one if you like, just to show that it's not going to stop. So don't end it, because it's still going. We don't know where it ends. All right. So let's see, interpreting position versus time graphs. So when you have a PVT, position versus time graph, steeper slopes, whether it's positive or negative, indicate faster speeds because we're looking at the slope. Negative slopes correspond to negative velocity and hence motion to the left. The slope is the ratio of the intervals, not the coordinates. So you can't just get the position and time and divide them. That does not work. You have to get the change in position. And then also the actual slope, which is just, you know, if you're looking at a graph and there's grids on it, you know, like that. I know from algebra you develop a bad habit, or some students develop a bad habit, and they just count. They go like 1, 2, 1, 2, and they would say 2 over 2, which would be fine unless these are units of 100. and these are units at 50. You got to pay attention to the scale, okay? So always use the scale. We're using the actual physical situation. So the mathematics of uniform motion. So now we're going to get some math put on it. I was going to talk, I think I already covered it. So, just for a line, when we talk for a constant velocity, again, this is position over time. And what we're doing is we're looking at the change in time, ti. So it's what I did earlier, and tf at some given point. And we don't care about the motion before it, but we can calculate the velocity. So we're just doing that again. That's all I was going to do. Let me just draw it on there. So, all right, I'm not going to go through it. I already did it. So we have that the velocity in the x direction or the y direction, it doesn't matter, is going to be the change in x, the displacement over the change in time. Yes? All right. So let's try to simplify this and see if we can get an equation. So we're just working from the definition of velocity to derive an equation. We're going to derive an equation. And this one's going to be pretty simple. So we have a Vx is going to be, the change in x is going to be x final minus x initial over time final. You know what, can I just leave the delta t? Because let's just assume that we're starting at time 0. So I'm going to leave delta t. Okay, what I want to do is I want to get an equation for the final position. That's what I want. I want something like that. Okay, so I got to solve for this variable. So what I'll do is I'll multiply by delta t. So I get Vx times delta t. So the velocity times the time is equal to xf minus xi. And now to solve for that, I just add this to the other side. So I end up with xi plus Vx delta t equals the final position. I'm going to go ahead and rearrange this because I like my single variable. I want it as a function. So my final position is equal to my initial position, but let me do a little sidebar here. The initial position is also called x naught, x0, the beginning position. So we're going to use that notation, x naught plus the velocity in that direction times delta t. But again, we usually start time at 0, so we could just say t. And this is our first kinematic equation. So the final position is given by the initial position plus the velocity times time. It's actually pretty simple. And what's nice is if you put your origin at the initial position, it's just the velocity times time. That will tell you the final position. All right, here's a quick little box. We're going to summarize some of the important stuff. So this is the constant velocity particle model, or just the constant velocity model. So if motion is moving at constant velocity, we get a motion diagram like this. And we covered that nicely in class. The displacement between successive points is equal for equal intervals of time. Mathematically, we get the velocity as the change, the displacement in the x or y divided by the displacement, or the change in time. And then we just derive this equation. So my position is equal to initial time plus the velocity times time. The limitation, the model fails if you have any kind of change in speed or direction. So any kind of speed or direction. Now when you're doing, when you're collecting real data, you're gonna have some change. So, when you'll see, when you collect real data, even for what appears to be constant velocity, it'll jump around a little bit. But that's not significant because we can fit a line to it. We can do our best fit, and we'll get a high correlation. And so we can consider that constant velocity. If this were to kind of spike out here and then come back up, yeah, that's a problem. So we'll talk about fitting lines and correlation and that sort of thing. Constant velocity motion, let's change this to, this should be x. Where I took these from, they used s for generalized. So for the position versus time graph, the slope of the position versus time graph tells me the velocity. And the velocity for constant velocity will always be a horizontal line, okay? There, so you need to remember that. All right, let's look at an example. And it's going to be one of those that we used to make jokes about these types of problems. So Bob leaves Chicago at 9 a.m. and drives east at 60 miles per hour. Susan, 400 miles away, leaves at the same time and travels west at 40 miles an hour. Where will they meet so they can have lunch? It's such a contrived situation. Like, somebody lives 400 miles away, you're going to call and meet for lunch? Yeah, I don't think so. Anyway, so let's talk about Bob. Let's start with just a little picture. So I'm just going to use a B for Bob, and he's in Chicago, and he's going to be headed east, so he's going in this direction. And they're going to meet somewhere. Okay, Susan is way over here, and she's going to go west, and they're going to meet somewhere. It's a bad picture. So it appears like somewhere in the middle, but I don't know where it is. It could be right here, or it could be way over here. I'm just drawing a picture so that I can start to make sense of it. Okay, let's see. Bob left at 9 a.m. and drives east 60 miles per hour. So we know his velocity, and I want to put a little b so I know it's the velocity of Bob is equal to 60 miles per hour. And we can leave it in miles per hour because we're dealing with hours probably. Coming the other way, we got 40 miles per hour. So the velocity of Susan is 40 miles per hour. What's the problem here, though? So think about that. You know, you can pause it and think about it. There's an issue here. And the issue is they're going in opposite directions. So both of these can't be positive. So we need to define which way is going to be positive. And what I'm going to do is I'm going to say this way is positive. We're going to use our traditional positive is to the right and up. So this is positive, and Susan is moving at a negative 40 miles per hour coming backwards. We also need to define an origin. So I'm going to go ahead, since we're just going to do it traditionally, I will say that this is 0 miles. And that means that Susan, she's 400 miles away, so this is going to be 400 miles. Okay? Now from this, I can get the initial position. So the initial position of Bob, that's an I, is 0. And the initial position of Susan is 400. All right, I think we're ready to start to attack it. It says where. The problem is that the only equation we have is the position function. X naught plus Vx times time. But here's the thing. When they get to this point, can't we say that Bob's position, final position, is the same as Susan's final position? Sure we can. So let's go ahead and do that. So we'll say that, let me scroll down a little bit. I'm running out of room. Bob's final position is equal to Susan's final position. Down here I'll show you graphically. And substituting this part right here in, we get Bob's initial position plus Bob's velocity times the time is equal to Susan's stuff. So her initial position plus her velocity times time. Time is going to be the same for both of them. They're going to be driving the same amount of time because they'll meet. So now we can just solve for t. So his initial position is 0, so that goes away. His velocity is 60, so we get 60t is equal to, her initial position is 400 plus her velocity, which is negative 40t. So now I can solve for t. We move this to the other side, so I add it, so I get 100t equals 400, so the time equals 4 hours. But that doesn't answer my question. It says where. So we can just use this. And we can plug 4 hours back into this equation for either of them. I'll go ahead and use Bob. So Bob's position, his final position, will be his initial position, which is 0, plus his velocity, 60, times the time, 4 hours. So we get his final position is going to be 240 miles. So they'll meet for lunch at 240 miles from Chicago. Yeah? 4 hours later, so at 1 o'clock. All right. You can also do this graphically. There's other ways to do it. You could set this up. You could have set up each equation, and then basically you're just solving a system of equations. I used substitution, but you can also do it graphically. So given these equations, we could have graphed the two position graphs and just found where they intercept, and that's where they meet. Pretty simple. All right, that's the constant velocity particle model. So we'll do this quick check, and then you can do the assessment. So which position versus time graph represents the motion shown in the motion diagram? All right, so let's see. So we see that it's the same distance, or the same displacements over the same time, so we know that it's constant velocity. Oh, but they're all lines. Okay, we know it's going left, so we know that the velocity is negative. Okay, so that one's out, that one's out, and that one's out. Okay, so we know that the initial position is off here somewhere. It's in the positive area. So we know that at time 0, the initial position needs to be up here. So our answer is D. And that's it.